Hello everyone. So I'm looking at the Unit 3 packet, and I know quite a few of us have been gone with matinees for the play, and so I'm going to talk through these concepts. I will say that, so we have proficiency target 1 and 2. This organization side, I'm going to have you just use the notes to fill these portions out. And so there's some slides where you can fill in those blanks. And then you will be able to write down the characteristics of metals, alkaline earth metals, transitions, metalloids, nonmetals, halogens, and noble gases. Okay? It's important for the quiz that you know where each of these groups are located on the periodic table, that you can distinguish between a group and a period, and knowing the characteristics of each of those that we had just identified. So if you do not have those notes filled out and you need that information, send me an email and I will send you the slides that you can look through. When we get to trends, though, we had a lot more discussion as a class. The first was an understanding of what atomic radius is. Because do you remember how we had orbitals around a nucleus? And those orbitals were areas of high probability where we could find an electron, but we don't know with certainty that an electron is right here. We just know that there's this area where there's a high probability. So to get radius, what we usually do is we put two of the same atoms close together, and we measure that distance between the nuclei, and then we divide that by 2, and that's our atomic radius. There's different trends for atomic radius, meaning we have, going down a group, the radius will either increase or decrease, and going across the period, it will either increase or decrease. One that you may already know that we talked about in the previous proficiency target is group 1 is called the alkaline metals. And as we go down the group, so the columns are the groups, we increased in reactivity. So as you go down this group, reactivity increased. So that would be a trend. Okay? And so we're going to think about atomic radius, and we hypothesized whether we went if we went down a group, if we would increase or decrease in atomic radius. So that's what I want you to do first, is I want you to come up with a hypothesis. And your hypothesis is going to say, going down a group. Okay, so going down a group, the atomic radius will blank. Will it increase or decrease? So you're deciding, okay? And so it will increase because, or it will decrease because, and then you give me a chemistry explanation. So I want you to hit pause on the video and write a hypothesis, and then once you've done that, come back. After a scientist has a hypothesis, the next thing that they do is they test that hypothesis. So in class, we had the atomic radii and picometers for each of these atoms. So lithium, potassium, cesium, sodium, rubidium. And so all of those are in period 1. And so I'm going to pull this up again for myself really quick. And we're going to write down the different radii. Okay. Right. So for lithium, we have a radius of 167 picometers. For sodium, it was 190 picometers. Potassium was 243 picometers. Rubidium was 265 picometers, and cesium was 298 picometers. As we went down this group from lithium to potassium to, lithium to sodium to potassium to rubidium to cesium, the atomic radius increased. And so take a moment and I want you to graph this. So here's the atomic number on the bottom and here's the radius in those picometers. And so pick axes that are going to work well, like the atomic number for lithium was 3 and for cesium it was 55. So figure out what your scale will be for atomic radius, atomic number, and then atomic radius. Some students chose to do bar graphs, other ones chose line graphs or kind of like scatter plots with the dots. So I want you to construct that graph. Okay. Hit pause and do that, and then come back when you're done. Once you've completed that graph, then I want you to ask yourself, does this experimental evidence support or refute your hypothesis? Like maybe you said the atomic radius will increase, and so that would support your hypothesis. But if you said the atomic radius would decrease, then it would refute your hypothesis, and we would need to make some changes. Now I do want you to consider something though. Lithium. So lithium has 3 protons in its nucleus, and in the first energy level it's got 2 electrons, and in the second energy level it's got 1 electron. Now I know this because it's in period 2, so that means it's got 2 energy levels. And the valence electrons are in the second energy level, and because it's in group 1, it only has 1 valence electron. Okay. Sodium, though, will have 3 levels, 3 energy levels, and its valence electrons will be in the third one, but it'll still only be 1 valence electron. So sodium, which has 11 protons, energy level 1 has 2 electrons, energy level 2 has 8, energy level 3 has 1 electron. This is what we are thinking is the main contributor to atomic radius. The greater number of energy levels, the larger that atomic radius. And if we think about this, it makes sense because these energy levels have multiple orbitals in them. And so we have way more orbitals, and we have these core electrons, these electrons that are closer to the nucleus than that one. And we know electrons repel electrons, so they're pushing this one away, further away from the nucleus. So as we go down a group, the atomic radius increases. So take a moment and write down any changes that you would make to your hypothesis. And then when you finish that, come back and we'll look at the next. Okay. Now we're talking about the radius going across a group. Sorry, group, I meant period, across the period. So the columns are the groups, the rows are the periods. So we want to see if we go from left to right, will the atomic radius increase or decrease, and why is that? So your hypothesis, you'd say going across the group, going across the period. Okay, so going across the period, the atomic radius, will what? You decide. Is it going to increase, decrease, stay the same? And then because, and then I want to see your chemistry knowledge explanation. Because the number of electrons increase, causing the overall radius to get bigger, or whatever your hypothesis would be. Okay, so fill that out and then come back and we'll look at the experimental evidence. Okay, so when we have, we know lithium, So this is 167 picometers. Beryllium is 112 picometers. Boron was 87 picometers. Carbon was 67 picometers. Nitrogen, 56 picometers. And oxygen was 48 picometers. Okay. So there's those. Just like before, I want you to use this data and I want you to graph that. Okay? Bar graph, line graph, scatter plot, however you're going to do this, but I want you to graph that data. All of these items were located in period 2. We went from lithium to beryllium to boron to carbon. And as we did that, lithium to beryllium to boron to carbon, the atomic radius decreased. So when you go down a group, the radius will increase, but when you go across a period, the radius decreases. Okay. Does this evidence support or refute what you were saying above? And then let's think about this for a minute. We drew the Bohr model for lithium. We said that there's 3 protons in the nucleus, and the first energy level has 2 electrons, and the second one has 1 electron. And then let's think about oxygen for a moment. Oxygen has 8 protons in its nucleus. The first level has 2 electrons, and then let's think about this second level. So oxygen has 6 valence electrons because it's in group 16, and those 6 valence electrons are in the second shell. So 1, 2, 3, 4, 5, 6. Okay. What's going on here is that 3 protons pulling on this 1 valence electron will not pull as strongly as 8 protons. Like 8 protons pulling on this 1 valence electron pulls a lot more strongly than the 3 protons. And so this is true for all those valence electrons. They're pulled more strongly into the nucleus. So this makes the overall radius smaller because the atomic number or number of protons was bigger. And we didn't have another shell. The valence electrons are both in the second energy level. It's just oxygen had more protons, which caused that attraction to be greater, making the atomic radius smaller. So update any changes that you would account for in your data. And then when you have done that, come back. If you want to, you can do the example problems. Now, we were looking at radius of neutral atoms, but what if it's not neutral? Like, what if an atom gains an electron? Well, that would make it a negative anion, right? Like those ions that are negative, those are anions. And turns out when you gain an electron, the atomic radius gets bigger. It will increase. Similar for cations. When you lose an electron, you become a positive cation. And the radius will decrease. Okay. So when you add an electron to make an ion, the radius gets bigger, but if you remove an electron, then the radius will decrease. Okay, that's the first trend you have to know. You have to know the trend for atomic radius. You need to know that as you go down the group, the atomic radius gets bigger, and as you go across the period, the atomic radius gets smaller. You also need to be aware that negative anions, ones that have gained electrons, become bigger, and positive cations that have lost an electron become smaller. The second trend you need to know is ionization energy. Ionization energy is the amount of energy needed to eject an electron from an atom. Okay, so the amount of energy the amount of energy needed to release or eject, okay, the amount of energy needed to release an electron from an atom. So if a nuclei has a high ionization energy, that means it would take a lot of energy to remove the electron. So like if this is the electron and this is the nucleus holding on to that electron, if it has a high ionization energy, it would take a whole bunch of energy to remove that electron. But if it's a low ionization energy, then it would be really easy. It wouldn't take a lot of energy to remove an electron. So what do you think going down a group? Do you think that it's going to become easier to remove an electron, which would be decreasing ionization energy? Or do you think it's going to become harder to remove an electron, and that would be increasing ionization energy? Same for a period. As you go across the period, is it going to become easier to remove an electron or decreasing in ionization energy? Or is it going to become more difficult to remove an electron, which would be increasing ionization energy? I want you to state a hypothesis for both of these, going down the group and going across the period, and make sure you include the because. All right? What's the chemistry knowledge that you're basing this on? I think that going down the group, the ionization energy decreases because. Or I think going down a group, the ionization energy increases because. Okay, so take a moment, hit pause, write down those hypotheses, and then come back and join us. Okay, now that we have those, let's look at our experimental evidence. You know what's really easy to see is these noble gases. Like here's helium, there's neon, there's argon, krypton, xenon, and radon. Okay, so helium, neon, argon, krypton, xenon, radon. And as we went down a group, we decreased in ionization energy. Okay, so going down a group, the trend is decreasing in ionization energy. Now let's look at a period. Here's a period right here. Lithium, beryllium, boron, carbon, nitrogen, oxygen, etc. This is period 2. And it's not perfect, but in general, the trend is increasing. That as you go across a period, the ionization energy increases. Okay, so one more time. As we go down a group, the atomic radius increases, but the ionization energy decreases. And as you go across a period, the atomic radius decreases, but the ionization energy increases. So does this experimental data, does it support or does it refute your hypothesis? Hypotheses, really, because you had more than one. Okay. Let's build Bohr models to discuss this. So lithium, let's write the electron configuration. We know how to use our periodic table and know that lithium is 1s2, 2s2, 2s1. 1s2, 2s1. Okay. So lithium, like we've been drawing, it's got 3 protons. Okay, 3 protons. Let's cover up where I drew the lithium, because we already know that this is the one that we're dealing with. Okay, so we got 3 protons, and energy level 1, because remember the numbers are the energy levels, so energy level 1 has 2 electrons in it. And energy level 2 has 1 electron in it. Fluorine has an electron configuration of 1s2, 2s2, 2p5. So fluorine has 9 protons, and the first energy level, okay, so this first energy level, it's got 2. The second energy level has got 5, 6, 7. Okay. And really, I didn't draw these great because we know that as we go across the period, the atomic radius decreases. And so like this one should have been maybe drawn a little bit bigger. Sodium, that electron configuration is 1s2, 2s2, 2p6, 3s1. So sodium has 11 protons. The first energy level has 2 electrons. The second energy level has 6, 7, 8. And then the third energy level has got 1. So when we go across a period, the ionization energy increases. It takes more energy. I have to add more energy to eject this electron. I'm going to make this one a little. It takes more energy to eject this electron than it is to eject that one. Okay. Now, why is that? Think about radius again. Here we have 9 protons pulling on the valence electrons in the second energy level, and we got 3 protons pulling on the electrons in the second energy level. And so it takes more energy to remove this one than to remove that one. But when we go down the group, now we have an entire new shell. And we have all of these inside core electrons that are pushing away this valence electron. So even though there's 11 protons, it's far easier to remove this valence electron. So going across the period, we increase in ionization energy, but going down a group, we decrease in ionization energy. Do you remember the electrostatic force equation? That force of attraction was equal to K, which was a constant, Q1 and Q2, which were charges, over the distance squared. So this attractive force and distance are inversely proportional. When the distance is big, that attractive force is weak. When the distance is small, the attractive force is strong. So this was the largest radius of these 3. And so the biggest distance is the weakest attraction. It was easiest to remove. It took the least amount of energy. This one was our smallest radius, and so it had the strongest attractive force. And so it took much more energy to release that one. Okay. Now, what if we remove more than 1 electron? Like, I'm going to draw a Bohr model for magnesium. So we got 12 protons. The first level's got 2. The second level's got 8. And the third one has 2. Okay, so to remove the first electron, okay, so to remove this first one, this ionization energy 1, I'm going to look at this table. The first ionization energy was 738 kilojoules per mole. Okay, so it took 738 kilojoules of energy to remove 1 electron from a mole of atoms. Now that this one's gone, if I try to remove a second one, it'll take a little bit more energy. Okay, let's see how much. Ionization energy 2 would be 1,451 kilojoules per mole. Okay, now if we try to remove a third one, ionization energy 3, something really interesting happens. These two are relatively the same. Like, it took a little bit more energy to remove the second compared to the first, but there's a huge jump when we get to the third one. We went from 1,000 to 7,000. 7,733 kilojoules per mole. Whenever you see a big jump in ionization energy, that means you got rid of all the valence electrons and you went in an energy level. As soon as you make that transition in, then the energy gets substantially bigger. It takes a lot more energy to remove that valence electron. Okay. And one of the last trends was electronegativity. Electronegativity is very similar to ionization energy. Like, ionization energy was how much energy it would take to remove an electron. Electronegativity is the affinity or the attraction a nucleus has for other electrons. Like, if we had two atoms and they were going to have a tug of war over an electron, which one would win, which one would lose? So the one with higher electronegativity could win that tug of war, where the one with lower electronegativity would lose. Okay? And so this is an electronegativity table. And so we could say, like, if sodium had, which is 0.9, had a tug of war with chlorine, which is 3.0, then chlorine is more electronegative, so it'd probably win that tug of war. Okay. Electronegativity has the same trend as ionization energy. So just like how going down a group ionization energy decreased, this was also true for electronegativity. And just like going across a group ionization energy increased, this was also true for electronegativity. But you'll notice noble gases are not on here. This is because their electronegativity is super low, because electronegativity is the affinity that a nucleus has to gain electrons. But noble gases are non-reactive. They're stable. They don't want to gain electrons. They don't want to lose them either. So their ionization energy is high. It'd take a lot of energy to remove an electron, but they have low electronegativity because they don't want to gain any new electrons. Okay, so we'll come back to reactivity in just a moment. One more time on our periodic table. Atomic radius increases as you go down, and it decreases as you go across a period. So atomic radius is the largest with francium, right? Because we get bigger this way, and we get smaller this way, which means bigger that way. And so this is where atomic radius is the biggest. Ionization energy, though, ionization energy, as you went down the group, it decreased. So as you go up a group, it would increase. And then we know as we went across the period that it increased. So if we're increasing and increasing, then ionization energy is the biggest with helium. This trend was the same for electronegativity. We went bigger as we went across the group, and we decreased as we went down, so we increase as we go up. But just don't forget that the electronegativity was super small for the noble gases because they don't want to gain any. So electronegativity is actually the biggest with fluorine. Metalloids are the separation between metals and nonmetals, and we know that this is kind of our metalloid line. So for the most part, atoms to the left of the metalloid line are metals, and atoms to the right are nonmetals. hydrogen is definitely an exception. It's a non-metal, even though it's to the left. And then we have metalloids that touch this line. In general, for metals, reactivity is the greatest with francium, that we tend to increase as we move from right to left, and we tend to increase as we go down the group. And it's the exact opposite for nonmetals. Noble gases are non-reactive, so that's why I'm not including them here. But in general, if you go across a period, the reactivity would increase. And then as you go up the group, the reactivity would increase. So the most reactive metal is francium, and the most reactive nonmetal is fluorine. There is a worksheet here if you want to do that. I'll just quickly show the answer so you could check your work. And then of course you can hit pause whenever and check any of these. Remember, you're going to be building a periodic table with your lab partner. That's the quiz. Okay? And so you need to be able to correctly identify different groups, like alkaline metals, alkaline earth metals, halogens, noble gases. You need to know the number of valence electrons in each of those groups. You need to know those reactivity trends. You need to know which ones are metals, nonmetals, and metalloids. You would also need to know which energy level the valence electrons are in. And that's just the period number. Like calcium has 2 valence electrons because it's in group 2, and those 2 valence electrons are in the 4th energy level because it's in period 4. Okay? And you need to know all those trends. So you need to know, going down the group, that the atomic radius increases. That's the end of the worksheet. That going across the period, the atomic radius decreases. You need to know that going down a group, ionization energy decreases, and going across the period, ionization energy increases. This is also the case for electronegativity. As we go down the group, the electronegativity decreases, and as we go across the period, the electronegativity increases, but not noble gases. Noble gases have really low electronegativity. And then you also need to be aware of reactivity. So in a periodic table, for metals, as you go down and then from right to left, that's where reactivity is the biggest with francium. But for nonmetals, it's the opposite. So as you go from left to right, you increase, and as you go up the group, it increases. So fluorine has the greatest reactivity. Okay, if you have any other questions, don't hesitate to reach out or sign up for a study session.